you were doing
No.
while you were doing it?
No, I never did that.
Me, until I stopped app hopping.
Okay. Hey. Look at those shoulders. To the beat, y'all. Yes, we're gonna do some calc today. Every day, Mahan, Mr. Mahan. Welcome in, dude. How's it going, man? Welcome back. Are you in summer? Is it summer for you, Mahan? Mahan. Nor Hashanalapur. My first attempt was real bad. Nor Hashanalapur. Oh, nice. You gonna plan for some internships, or are you gonna try next year? You just finished your freshman year, right? I never did any internships. I just went home and hung out with my friends, and then went back to school, and then because I was working during the summers, I would go home. For my first year at college, when I went away, I came back. Well, I always worked. I worked at a pizza place through high school. I made a lot of pizzas, delivered pizzas. I did everything kind of. I like. It was kind of a, you know. That's what I did from like 17 to when I left for college after community college. When I left for university, and then I got a job at like a data processing center the summer after my the summer I got there, and then I quit that job because I started school that fall, and I was like, dude, I can't do the both. This is gonna be tough. So I quit that. I got like, sorry, peace. I get out of here. Yeah, and then and then I got a job as like at another restaurant a year ago later after I got more comfortable. No hasi and alapu. Oh no, por. Nor hasi and alapor. I think I got it. Yeah, dude, I wouldn't. I would. I think the hardest part for me about if I went like abroad somewhere for like a vacation would be I just would get wrecked by pronunciation. I'm just so like white when it comes to like pronunciation and words. I was planning to, but it's too late to apply now. Next year for sure. Doing project stuff, giving fix me. Yeah, that'd be good. Did you ever finish those projects you were working on, or did you submit those for your classes? All right. Let's kind of get things loaded up here while we're talking. Yeah, that NBA clip we watched yesterday, they they didn't like do anything bad. They just flagged my video as like can't be monetized because for just like that like those skipped around clips we watched of it. It was just crazy. So I just cut it out. YouTube lets you just automatically lets you cut it out. So I just said, all right, cut it out. Let me grab the chat here. Pop out the chat. I gotta start the switch. All right. Ahan. Nice. Yeah, that's how I'm getting with my projects. I'm like, we gotta keep chugging along, man. It's hard to, when it's like really, it's you get like a lot of motivation right at the start, and then you get it going, and you get it working, and then to like kind of wrap it up, it's like, yeah, I feel you for sure. Okay. All right. Keep forgetting we got notes. All right. I need my drink. All right, we're going to get going here, back again into Calculus 1. Hello, everybody. Welcome back in. I didn't really say hello. Today is May 22nd. 22. Peace ups. Today is May 22nd. It's a good day. I started going on my product again. Another cycle of the product build. So it was a busy day back at the lab. I was in the lab a lot today, let me tell you. So when I start to build my products, you know, before you normally in these manufacturing processes, a lot of the times you build kind of a what's referred to as like a pilot. Like you often see them as TV shows. Like the first episode is a pilot episode. It's kind of like a tester, right? Just to see if it's if your current like formulation or whatever is feasible. And so I was going on doing that process over the past 2 days, and so basically building a mini product, and then we'll put them through some various testing and things like that, and yeah. So, but it was a lot of work today. Let me tell you, a lot of work today. So tomorrow will be easy. Friday, I got a little bit of work to do in the morning, and getting things into the testing, and into like some certain conditions and stuff. So. Yeah, but should be a chiller afternoon where I can kind of just do some busy work. Aurora Sor, dude. I just keep making new projects. Me too, dude. My repos just keep growing, but the finished ones just keep growing. Unfinished ones do too, proportionally. Yeah, I see your pull requests onto the small business manager. You've been busy on that, dude. Nice. I appreciate it, and I really like the contribution. So we'll have to go over those requests probably this weekend, like we usually do. We do the pull requests on the community projects on the weekends. You gave like a really detailed thing I saw. So regarding like PyCharm and stuff like that. So we'll have to like merge it into dev and test it out and see what's going on, and yeah, like we did last time. You guys aren't familiar, we have the Small Business Manager community project. So if you want to be a contributor to the project and kind of be involved and potentially, you know, have that be like a staple on your potential, if you're looking for, you know, maybe having some projects on your belt for your portfolio or whatever, I have no problem with you if you're a contributor to that, to list that you contribute on that as like a small little sub bullet point or whatever you want, because it's a community and we're all doing it together. So yeah. Yeah, and the business owner, she gave you us all permission to do whatever we want with it. All right, let me grab a drink real quick and we'll get going. If you guys are here, let's get a like and we'll get going into some Calc 1. All right, let me grab a drink. Alright. You got, hold on. I gotta get a paper towel or something. Alright. I'm taking some jet fuel. It's like glowing. That's funny. Let's put that down here. I'll give it a shot. Jar of piss in the window. You guys ever? These were on sale at Costco. Remember these from back in the day? Go-Gurts. It was like $5 for like a 60-pack. Heck yeah. All right, you guys can't be like give me assistance how I eat. Go-Gurt. All right, Coach Mo. How's it going? I had some old projects to be done with the lines Mac, but I just gave up. Hey, Coach Mo. Math's fun. What do you mean? Come on, Coach Mo. We solved the world. We're gonna figure out the secrets of the world here. Let's try. Yo, Python crash course? You been doing PCC, Coach Mo? Have you been watching the try it yourself videos? Take advantage of those. Hey, Famish Edits, how's it going? We're gonna get into some calculus here. We're gonna get back. I'm just enjoying a little Go-Gurt flashback to the past. You guys remember these back in the day? Go-Gurt. Nah, dude. Biochemists, they just use like Excel a lot of the time. How I like, and honestly, it's a lot of these companies are still on Excel. There's like, there's bioinformatics, which those people program a lot more. But I'm trying to. We'll see what happens. I've been learning programming and teaching myself math, and yeah. I'm doing a review on calculus now. It's been 7 years, 6-7 years. All right. We're still on this square here. So we watched all those, right? We're on lesson 5, properties of limits. We accidentally skipped ahead. We got kind of confused yesterday. So we already watched this guy. Okay, I think we're on this one here. So this one has a couple of practice problem stuff, so I like the ones with practice problems. All right.
Let's find the limit of f of x times h of x as x approaches 0. All right, we have graphical.
Yeah, Vance, you got to keep up, my boy. Let's go. Get back in here.
H of x. And we know from our limit properties that this is going to be the same thing.
What's Go-Gurt? Like ice juice? Wasn't that when you were a kid, Mike? Go-Gurt is just like tube yogurt. It's yogurt on the go. Go-Gurt. Yeah. Yeah. They just taste like like smoothies, honestly. Oh, Fluent Python. Coach Mo said, nah, man, I'm beyond that Python crash course. No. Fluent Python. All right, I got you, Coach Mo. Yeah, I got to get back into that. We started reading back. We're on and off, man. We're all over the place on content here. I'm trying to just keep it fresh for y'all. Keeping it fresh. All right, let's kind of, let me get chat pulled up over here so I don't have to. Okay. I think I can teach myself. I just got to prove it, what I know and what I can do. Yeah, Famish, that's what we're doing here. We've been doing that for 11 months now. We teach ourselves programming. We've come a long way, made a lot of really cool projects. You can go to my website, michaeldeming.com, and check out my projects there. I have all of them listed in a demo, and you can join my Discord and see everything. It's a really great site. Check out my portfolio there. I should put like a little, let me do like a little, let me take the link and, well, I don't think I can. And then I'll pin my portfolio. There you go. Now you guys can check out the port. And I'll do it for the Twitch as well. We'll pin that. All right. Cool. Let's go. If you guys aren't subbed along, feel free to sub along. All right. Let's get going here. Hey, Diarya, how's it going? Am I pronouncing that right? Diarya. I think I am. I don't know. Let me know. So hopefully I am. Boy, do I have a story to tell you about my calc teacher. Do I have a story to tell you about my calc teacher? I can tell you guys if you want, but me and her, we had a hard time getting along. All right, let's get into it. We got to get moving.
As x approaches 0 of f of x times the limit as x approaches 0 of h of x. And let's think about what each of these are. So let's first think about f of x right over here. So an f of x, as x approaches 0.
Okay, so as x approaches 0 from both directions, we don't have any positive or negative implication here. So we are converging on a limit of -1 here. But we're multiplying that by h of 0, h of x, which is here as x approaches, which is 1. So -1 times 1. Obviously, it's going to be -1.
Notice the function itself isn't defined there. But we see when we approach from the left, we are from the right. The limit here seems to be x approaches 0 as we equals 0 approaching 1. Approaches is a continuous. 1 is 1.
Woo!
All right.
We're cooking now, boys. We up here.
Continuous functions. So we have the limit as x approaches 0 of h of x over g of x.
I was like, it can't be that simple. But it was. All right. We're doing division here. Quotient property of limits. So we're approaching 0 from both directions. So we're coming in. Oh, coming up here. 4. Oh, we're up here at y equals 4. All right, we are continuous here, so we're all good. We don't have to be really continuous. I mean, we can have a limit without being. I don't know. I'm not getting too ahead of myself here. I'm just learning here. But there is no. They both approach this limit. Okay, and we're multiplying that by, it looks like 0. Or we're dividing by g of x as 0, so this is undefined?
Our limit
Or this does not exist? Or what is this?
The limit of h of x.
Can't divide by 0 here.
Approaches 0 over the limit of g seems to be approaching 4. And as we approach x equals 0 from the right, our function is top to 0 from, because it's continuous. So this also.
What does he say about continuous?
Which happens approaching 0 and continuous function. So the limit as we approach is 0. This is, let's see, as we approach 0 from the left. As we approach x equals 0 from the left, our function seems to be approaching 4. And as we approach x equals 0 from the right, our function seems to be approaching 4. And that's also what the value of the function is at x equals 0. That makes sense because this is a continuous function. So the limit as we approach x equals 0
continuous meaning it doesn't have a gap. Yes.
Should be the same as the value of the function at x equals
So
0.
coincidentally,
4.
remember that's not always true.
As x approaches 0. So from the left, because it's continuous, 0. So we can't divide 4 by 0.
Yes.
So this whole entire limit
does not exist.
Woo! And actually, if you were to plot h of x.
All right. What does he say?
Over g of x, if you were to plot that graph, you would see it even clearer that that limit does not exist. You would actually be able.
Nice. Coach. I was wondering who was gonna notice. Vance was the first one to notice. Congrats, Bench, for paying attention. I had the best calculator from Professor I had Boris in university. It's so funny. Writing notes in a notebook helps to digest math and programming. Doing calc spectrometry in your mama. I gotta go out and learn cybersecurity on my own right now. The concepts, at least. I'll see you in the future. All right, see you, Vanch. See you later, man. I gotta keep my TTS or I get lost in chat. Okay.
We are asked to find these 3 different limits. I encourage you, like always, pause this video and
Okay, try these yourself. Find the limit of, as x approaches -2, of f of x plus g of x. So as x approaches -2 on this graph, this limit does not exist, right? And as g of x approaches -2, this also does not exist. So we do not exist here. Okay, as x approaches 1, f of x plus g of x, well, this does not exist as x approaches 1, right? Because we don't have any direction implication here, so it's just coming from both directions. And then we're adding g as g approaches 1, so that would be 1. So we're doing does not exist plus 1. Well, if you do does not exist plus 1, is that even possible? We'll find out. We haven't seen an example of that yet. And then we have f of x times g as x approaches. Does it look to be
do it yourself before we do it
1? So
Mahan says the hardest type is compositions.
okay, so here, yeah, we'll see here.
So when you do this first one, you might just try to find the limit as x approaches -2 of f of x, and then the limit as x approaches -2 of g of x.
That's what we did.
And then add those 2 limits together. But you will quickly find a problem. Because when you find the limit as x approaches -2 of f of x, it looks as we are approaching -2 from the left, it looks like we're approaching 1. As we approach x equals -2 from the right, it looks like we're approaching 3. So it looks like the limit as x approaches -2 of f of x doesn't exist. And the same thing's true of g of x. If we approach from the left, it looks like we're approaching 3. If we approach from the right, it looks like we're approaching 1.
That's what I was thinking.
It turns out that this limit can still exist. As long as the limit as x approaches -2 from the left of the sum, f of x plus g of x,
exists. So you can cherry pick.
And is equal to the limit as x approaches -2 from the right of the sum, f of x plus g of x. So what are these things? Well, as we approach -2 from the left, f of x is approaching, looks like 1, and g of x is approaching 3. So it looks like we're approaching 1 and 3, so it looks like this is approaching, the sum is going to approach 4. And if we're coming from the right, f of x looks like it's approaching 3, and g of x looks like it is approaching 1. And so once again, this is equal to 4. And since the left and right-handed limits are approaching the same thing, we would say that this limit exists, and it is equal to 4.
Interesting.
Now let's do this next example, as x approaches 1.
Okay, let's try this.
Same.
As x approaches 1, right, for f of x on the left, we have, as x, we're approaching 1 here. From the left, we are coming up on a value of 2, and then from the right, we're coming up on a value of 1, so that'd be 3. And then here, as g of x plus g of x as we approach 1, well, that would be 1. Well, those don't add up together to be the same thing, being that this doesn't exist altogether. So does that mean that this
once
doesn't
again,
exist?
if you look at the individual limits for f of x, the left-hand side of f of x plus g of x,
says, what are you trying
what
to
is that
build?
going to be equal to? As
We're
we
learning.
approach- so f of x, as we approach 1 from the left, looks like this is going approaching 2. I'm just doing this for shorthand. And g of x, as we approach 1 from the left, it looks like it is approaching 0. So this will be approaching.
Oh, sorry, my bad. You add up the f of x plus g of x of the left and f of x g of x plus the right. You don't add up the f of x and of the right and then g of x of the left and right. So in this case, let's pause there. Let's try again. From the left here of the f of x, we're coming in and we have a limit of 2, and then for g of x we have a limit of 1, or sorry, there's a limit of 0. So we're going to be a sum of 2 for it coming from the left for this limit, and then coming from the right we have a limit of on f of x of -1, and then we have a limit of 0 here.
2 plus
Okay,
0,
so here
which
we
is
go.
2.
Let's see what happens
And
here.
then the limit is going to be equal to, well, for f of x, as we're approaching 1 from the right hand
Negative
side,
1,
aren't approaching
0.
the same value.
So these
this
aren't
one
approaching the same value.
does
So that one
not
does not exist. Okay.
And then
Gotcha.
last but not least, x approach.
Okay, so now let's try this one. So f of x times g of x. Okay, so f of x times g of x as we approach 1.
Says, oh, you're learning Calc 1.
Yes, sir. So as f of x times g of x as x approaches 1. So from the left, we come in and we have, from the left we come in and, sorry, my brain's just like stopped working. So we're coming in onto 1 for f of x, sorry, yeah. So coming in, we have a value of 2 here. And so, and then same thing, so basically we have 2 times, so we have 0, and then we have negative 1. So we would actually be multiplying here, so 2 times 0 is 0. And then we would be multiplying negative 1 times 0, so that would also be 0. So this limit would exist at 0.
F of x times g of x, it use a value. And so this is approaches. But limit exists. We get interesting examples because sometimes when you think that the component limits.
All right. Not too shab. Okay. So this is less than 5 properties of limits. Okay, so then when performing operations on limits. Okay, so we'll have to think of how we want to word these notes. Practice problems. Let's go. Are you guys ready? Get your guys' types ready. Get your chat ready. Here we go. Practice problems coming up. Practice problems coming up. Man, give me on the. If I grew up playing the sax. Man, get me on the stage. Low lighting. Yeah, I got it. Hold on. Alright, let's keep it moving. Keep it moving. Chill, 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 chill. Alright. We all love some good jazz. We know, we know, we know. Alright. If I made this silent, can you guys not hear? Oh, you guys can't hear. Yeah, good. Alright. For this problem, function h is graphed. Find the limit of 0.5 times h of x as x approaches -3. Okay? So let's look up to our notes here. We know we have the sum property, or the product property, applies to constants in the function, right? So we just find the limit of h of x as we approach -3, and we multiply that by a value of 0.5, if I am understanding this correctly. So h of x is this graph here. We're going to find -3, and as we approach that value, we are converging on a limit of 4, right? We are multiplying that by 0.5. So I'm going to say that that is going to be a big D. What you guys think? What do we feel? What do we feel? What do we feel? What do we feel? Do we agree? I'm scared to submit here. Ah! Woo! Functions h and g are graphed. Function h and g are graphed. Alright. Find the limit of h of x plus g of x as x approaches -3. Okay? So h of x as x approaches -3. Oh, what happens again with the what happens here with the as x approaches -3 for this function? The value is on -3, but we don't want to know what's on. We want as we approach that. So we would be approaching a y equals 3, not a 0, right? At least for this graph. So this would be 3 in this case, I believe. Yes, exists at this point. Does not exist at this point. But we don't want to know what the limit at this point is. We want to know as we approach, right? So we're coming in, as we approach, it looks like we're converging on a value of 3. We don't know necessarily what this would be, but we do have the graph. If I understand this correctly. So then, where g of x, as we approach -3, converges on 2. Okay, so we're doing 3 plus 2. Do we agree on another big D? What do we think? Do we think here? I say 5. Ooh. Woo. Let's go. Let's go. Okay, function g is graphed. Yes, sir. He's right there with us. Alright, function g is graphed. Find the limit as x approaches 0 of 2 of g of x. 2 times g of x. Alright. So we have the g of x as we approach 0. For this graph, it looks like from the left and the right. Hey, Blankers. Appreciate you coming in, dude. Thanks for stopping by. How are you? I hope you're well. Thank you, man. Alright. So for this one, I'm saying that this does not exist. But for constants, can you... Let's actually do this. Can we say, what if the limit from g of x 2, that would be, from the left would be 1, and this would obviously be 3. So 1 times 2 would be 2, and 2 times 3 would be 6, so those are not equal. So I say this still doesn't exist. What do we think? Yes. All right. The functions f and h are graphed. Okay. Find the limit as x approaches -1 of f of x minus h of x. Okay. Well, as x approaches -1 for f of x, we are converging on a limit that does not exist, at least in this first case, and also for h. So let's then find the individual sides and apply them, right? So, h of x coming in from the left, or f of x, I'm sorry, we have a limit of 2. And f of x coming in from the left, h of x coming in from the left, we have a limit of 1. So 2 minus 1 is 1 for the left. Now we will see if that equals the limits on the right. So for f of x, we're coming in at 1, and we're minusing 0 from that. So this has a limit of 1. Let's go. 4 for 4. Give me a Wendy's over here. Call me Wendy's. Wendy's. All right. Hey! Proven skills. Limits of combined function groups. Ready to practice. All right. We got 4 more problems. All right. Ready, guys? Here we go. We need some like hype music. Biochem, degree in biochem, I guess, but programming, 11 months for programming. We need some like hype, something hype. All right, let's go, boys. Let's go. Let's go. All right. Functions f and g are graphed. We're taking off here, boys. Functions f and g are graphed. Find the limit of f of x divided by g of x as x approaches -1. All right, here we go, guys. Okay. So as we approach 1 here for f of x, we have, this doesn't exist. And as we approach g of x for 1, okay, so we're going to have to do some combinatoric combined functions here. So coming in from the left here for f of x, come on, you're messing me off the scenes. Get behind the scene messages. Get messages behind the scenes. Functions f and g are graphed. Okay, so f of x coming in from the left has a limit of 4, and g of x coming in from the left has a limit, coming in on 1, has a limit of 1. So 4 divided by 1 is 4 from the left, right? So keep that in mind. 4. So 4 on our left hand. Coming in from the right on g of f of x, we have a limit of 3. And coming in on the right for g of x, we have a limit of 1. So we have 3 divided by 1, which is 3. So this does not exist. I say this does not exist, friends. What do we think? E does not exist? Oh, you guys can't really see that well, because these things are so dang big. Pause. I wish I could drag this, make it smaller. What do you think? Do we see D and E? Does not exist for this one? Right, this is 4 on the left. This would be 3 on the left. This would be 1 and 1. So 4 divided by 1, 3 divided by 1 do not equal each other. Does not exist. Haha! Let's go. Next question. Functions h and f are graphed. I'm feeling this. All right. We want to find the limit of h of x times f of x as x goes to -1. So h of x as x goes to -1. We have a limit of 2 here from the left, and we also have a 2 on the right. So this does exist here at 2. We then have f of x as we go from f of x as we come in from the left, as we approach -1, has a value of 4. So we want to multiply those by each other. 4 times 2 is 8. 2 is 8. What do we think? 4 times 2 is 8. Well, dang, we needed like a beat drop right there, but it went to like a bridge. What do we think? Do we think 8 on this one? Come on, calc boys. Come up, calc boys. Where the calc boys at? Do we say 8 on this one? H of x times f of x as x approaches -1. We have 2 for f of x. We get 4 for, or sorry, for h of x, we have 4 for f of x. All right, I'm gonna say 8 here. Come on, don't kill the vibe. Ooh. Yeah, we should have hit that one on the drop. Okay, hold on, maybe we can get this one. We're graphed here. Oh, we're too late. Oh, come on. Come on. Oh, this one's crazy. This one's crazy. Functions h and g are graphed. All right. H, as we come from the left, 4 for h. As we approach 0, g, 0. But we can't do that. Does not exist here. Do we see does not exist for this one? It's the piss jar. It's the Mountain Dew, man. Let me tell you. Swarge, how's it going? I'm just feeling the calc today, boys. No. We got Mountain Dew. We're feeling good. Ooh, let's go. Come on. All right, next question. Function h and g are graphed here. We need to find the limit of h of x times g of x as x approaches 3. All right, calc boys, let's cook here. Let's go, calc boys. H of x as x approaches 3. We got, we're coming in from the left. This doesn't exist. We need to do it from the left here. So we're coming in, we got 1. So 1 times 5. So the left is 5. The right is going to be 5 times 1, 5. So we got 5 here. Come on, what we got? Oh, Swear says C. It says 3. Let's check it. 1 times 5. 5 times 1. I'm getting 5 here. What are you getting? 3. Ah, Swaraj, sorry, man. All right, let's go over this one. So we come in, the limits on both of these as we approach 3 themselves doesn't exist. So we need to use combined functions here to evaluate from both sides. So we have from the left here, as we approach on h of x, we have a limit of 1. And as we approach on g of x, we have a limit of 5. So 1 times 5, due to this function, right, or this equation, is 5 for the left. For the right, we're approaching here on h of x is going to be 5 for the limit times 1. So 5 and 5 for both sides. Boom. Hey, Swaraj, thank you. Yeah, we got to, we'll get there. All right. Oh, that was 4 for 4, boys. Let's get some hearts in chat for 4 for 4. Call us Wendy's. We gotta have like a Wendy's emoji or something. I gotta get like a Wendy's emote, so we can when we go 4 for 4, we can throw the Wendy's up there. Baman Akash, do you want me to go over it again? We can go over it again here. I don't mind. I'm feeling good today. Do you guys want me to turn down the music a little bit so we can chat a little bit better? I feel like we're in the club. We're in the club. All right. Woo! Fo fo fo! Wendy's in chat, guys. Wendy's.
Hey everyone, this is Tatiana Manning, host of Real Talk with PG&E. We
Oh, no.
businesses are dealing with rising costs and looking for
All right, we got a video up next. We got to pause tunes. Whoo! All right, let's take a breather here. You know, sometimes you got to step outside the club. You got to take a little breather. Yeah, you got to refresh. You got to look yourself in the mirror before you go back in. All right, let's go back. Let's get this. All right, up next is a video. Here we go. 3 minutes. Not bad. Not bad.
Composite functions, or at least a way of thinking about limits of composite functions. And in particular, we're going to think about the case where we're trying to find the limit as x approaches a of f of g of x. And we're going to see under certain circumstances, this is going to be equal
nested
to
function
f of the limit as x approaches a
of g of x.
G of x. And what are those circumstances, you are asking? Well, this is going to be true if and only if two things are true. First of all, this limit needs to exist. So the limit as x approaches a of g of x needs to exist. So that needs to exist. And then on top of that, the function f needs to be continuous at this point.
Swearage says bro is L hospital rule done.
Continuous at L. So let's look at some examples and see if we can apply this idea, or see if we can't apply it. So here I have two functions that are graphically represented right over here. Let me make sure I have enough space for them. And what we see on the left-hand side is our function f, and what we see on the right-hand side is our function g. So first, let's figure out what is the limit as x approaches -3 of f of g of x. Pause this video and see, first of all, does this theorem apply? And if it does apply, what is it?
Okay, so does this theorem apply, meaning that the limit at g of x has to exist at -3, right? So at -3 for g of x, the limit does exist here at 3, okay? The value here of the function exists at -2 for -3. Oh, yeah, we are going -3, yeah. But the limit is 3. So then, so that checks, and f is constant at that limit. So at 3, f is constant. It has a at the limit 3. So at the limit 3, f is constant. So we do have a value. Do we take that value then of that limit at 3 and say, okay, 3 times whatever the limit would be? 3 times 3, is it 9?
So the first thing we need to see is, does this theorem apply?
No, f of g of x. We're multiplying. We're taking f of g of x.
So first of all, if we were to find the limit as x approaches -3 of g of x, what is that? Well, when we're approaching -3 from the right, it looks like our function is actually at 3. And it looks like when we're approaching -3 from the left, it looks like our function is at 3. So it looks like this limit is 3, even though that value condition. And then the second question is our function f continuous at this limit, continuous at 3?
Okay.
So when x equals 3, yeah, it looks like at that point our function is definitely continuous. Yeah. And so we could say that this limit is going to be the same thing as this equals f of.
So we say f of 3, and so that you take the value of f of 3. Oh, okay, got you. Take the value of f of 3, which would give you -1.
The limit as x approaches -3 of g of x, close the parentheses, and we know that this is equal to 3, and we know that f of 3 is going to be equal to -1.
Gotcha.
So this met the...
Woo! Okay. Makes sense, makes sense. Another vid coming up.
In a previous video, we used this theorem to evaluate certain types of composite functions. In this video, we'll do a few more examples that get a little bit more involved.
Ooh.
So let's say we wanted to figure out the limit as x approaches 0 of f of g of x. F of...
Okay, so the limit of f of g of x as x approaches 0. So we first need to figure out what is the limit of g of x at x equals as x approaches 0. So on g of x as x approaches 0, we have a limit of, I'd say, 2, right? We could do maybe delete code. The math is it spices my brain up, Tim. If you're nice to me, Tim, Mr. Tim. Right? And so then, okay, and so then we have, so that is what the limit is at 2. So then we want to find, is the function of f continuous at 2? And no, it is not continuous at 2, right? Well, we have a value here, so does that technically mean that it's continuous? Like the line does have a gap, but you have value for 2 at 3, right?
G of x.
So I'm wondering.
First of all, pause this video and think about whether this theorem even applies.
It applies.
G of x.
Well, no, hold on. Well, we're trying to figure out this part. We need to figure out the f, is it continuous?
If we meet this first.
Does continuous mean that it can't have no gap? It has no gap? Or can it have a gap as long as it's filled elsewhere?
Condition. So if we look at g of x right over here, as x approaches 0 from the left, it looks like g is approaching 2. F continuous at that limit, at 2.
Okay.
So when x is equal to 2, it does not look like f is continuous. So
okay,
we do
so
not
no, you cannot, if you jump on a gap, it is not continuous. Got you. Got you. Okay, so this is not continuous. You have to just keep going in that direction, or that, like that, I guess that vector path or whatever of that's where we're going, right? If you have that jump, it can't, even though you're filled, can't, doesn't work. So now what does this mean?
Second condition right over here, so we can't just directly apply this theorem.
So we can't
just because you can't apply the theorem does not mean that the limit doesn't necessarily exist. For example, in this situation, the limit actually does exist. Okay. One way to think about it, when x approaches 0 from the left, it looks like g is approaching 2 from above. And so that's going to be the input into f. And so if we are now approaching 2 from above, here's the input into f, it looks like our function is
Whoa, what was that? Back it up, back. Above? What?
From the left.
Wait.
It looks like g is approaching 2 from above.
Okay, yeah. G is approaching 2 from above. We're coming down at that thing. Okay?
And so that's going to be the input into f. And so if we are...
So that's going to be the input into f.
Are now approaching 2 from above. Here's the input into f.
So this is where he's losing me. What's he doing right here? He coming in from the left, and why are you evaluating this at the... What are you doing here?
Is approaching 2 from above. And so that's going to be the input into f. And so if we are now approaching 2 from above, here's the input into f.
Is above a synonym from the right?
Approaching 0. And then we can go the other way. If we are approaching 0 from the right, right over here, it looks like the value of our function is approaching 2 from below. Now if we approach 2 from below,
it's a bad color
it looks
to
like
use.
the value of f is approaching 0. So in both of these scenarios, our value of our function f is approaching...
Okay, Con, you lost me there for a second, but you got to tie it up there. Okay, so if the function, if this doesn't apply, we can still find a limit by evaluating the direction of g of x as we approach that limit. So, bro, he's coming in from the left here, and then it reciprocates on the when you input it into f.
going to be the input into f. And so if we are now approaching 2 from above here as the input into f, it looks like our function is approaching 0. And then we can go the other way. If we are approaching 0 from the right over here, it looks like the value of our function is approaching 2 from below. Now if we approach 2 from below, it looks like the value of f is approaching 0. So in both of these scenarios, our value of our function f is approaching 0. So I wasn't able to use this theorem, but I am able to figure out that this is going to be equal to 0.
Okay, kill my vibe here, Con. So he arbitrarily chooses to evaluate G by coming at it from the left. And he recognizes that when I come at it from the left, I am above the function. I swear to God, I can explain this better. Yeah, a lot of people are seeming to not understand this or having trouble with this one. Okay, so
Now let me give you another example.
let's look at another example.
Let's say we wanted to figure out the limit as x approaches 2 of f of g of x.
Okay, so as x approaches 2 of f of g of x. So as x approaches 2 of g of x, the limit does not exist on g of x.
Pause this video and we'll first see if this theorem even applies. Well, we first want to see what is the limit as x approaches 2 of g of x. When we look at approaching 2 from the left, it looks like g is approaching -2. When we approach x equals 2 from the right, it looks like g is approaching 0. So our right and left-hand limits are not the same here, so this thing does not exist. Does not exist. And so we don't meet this condition right over here, so we can't apply the theorem. But as we've already seen, just because you can't apply the theorem does not mean that the limit does not exist. But if you like pondering things, I encourage you to see that this limit doesn't exist by doing very similar analysis to the one that I did for our first example. Well, we first want to see what is the limit as x approaches 2 So it looks like this is going to be equal to 2. So that's a check. Now let's see the second condition. Is f continuous at that limit, at 2? So when x is equal to 2, it does not look like f is continuous. So we do not meet this second condition right over here, so we can't just directly apply this theorem. But just because you can't apply the theorem does not mean that the limit doesn't necessarily exist. For example, in this situation, the limit actually does exist. One way to think about it, when x approaches 0 from the left, it looks like g is approaching 2 from above. And so that's going to be the input into f. And so if we are now approaching 2 from above here as the input into f, it looks like our function is approaching 0. And then we can go the other way. If we are approaching 0 from the right over here, input into f. And so if we are now approaching 2 from above here as the input into f, it looks like our function is approaching 0. And then we can go the other way. If we are approaching 0 from the right over here, it looks like the value of our function is approaching 2 from below. Now if we approach 2 from below, it looks like the value of f is approaching 0. So in both of these scenarios, our...
Okay, I think I get it. So he just evaluates, okay, so when I input this into the function, right, the limit here as I approach 0 for x, well, I'm getting a value of, I'm approaching this from below. I have a negative slope, or like above, I'm coming at it from above. So I would then evaluate this function here and come at it from above the function, which happens to be coming from the right direction. Now, if coincidentally this function had a positive slope and I was looking at it from that way, coming at it from the left, well, that would say, okay, now I'm coming at it from below. So then I would be coming at it from, and if this was like this, then I would be coming at it from that way. But because on this function I have a slope of downward, I'm going to be coming at it from above, the above side of this function. I'm coming at this from above, so I'm going to come at this from above, which happens to be coming at it. As I travel, like these 2 points, they meet coming up to here. Okay. Okay. Gotta keep moving.
All right.
We're already doing this an hour.
All right, let's get a little more practice taking limits of composite functions. So here we want to figure out what is the limit as x approaches -1 of g of h of x. And the function g, we see it defined graphically here on the left, and the function h, we see it defined graphically here on the right. Pause this video and have a go at this.
Hold on. From below means he's using the y value of g of x. From below means he's using the y value of g of x as the input for f. The y value. Okay, so then, okay. Let's keep going.
All right, now your first temptation might be to say, all right, well, what is the limit as x approaches -1 of h of x? And if that limit exists, then input that into, pause this video, g, the limit as x approaches -1 of g of h of x. And the function.
Okay, so I want to get out my little notebook here. So let's think here. So the limit of g of h of x as x approaches -1. So first off, let's find what the limit of h of x is, right? So the limit of h of x as x approaches -1 is equal to, and in this case, as x approaches -1, the limit here, oh god, here we go. Another one of these cases here. Internal limit that doesn't exist. This one doesn't exist. So are we going to evaluate these on a case-by-case basis, or interesting? So if this one doesn't exist, coming in, then we say, well, if we're coming at it, let's see.
G, we see it defined graphically here on the left, and the function h, we see it defined graphically here on the right. Pause this video and have a go at this. All right, now your first temptation might be to say, all right, well, what is the limit as x approaches -1 of h of x? And if that limit exists, then input that into g. So if you take the limit as x approaches -1 of h of x, you see that you have a different limit as you approach from the right than when you approach from the left. So your temptation might be to give up at this point. But what we'll do in this video is to realize that this composite limit actually exists, even though the limit as x approaches -1 of h of x does not exist. So how do we figure this out? Well, what we can do is take right-handed and left-handed limits.
Okay,
Let's
right-handed and left-handed
first
limits.
figure out what is the limit as x approaches.
So overall, the limit, this does not exist in itself, right? But the composite function, it does exist. So let's evaluate even further and expand this out to a right, to a left and a right.
-1 from the right-hand side.
Okay, right. So we have the limit of x approaches -1 from the right-hand side of what, h of x?
Of g of
g of h of x.
of h of x. h of x. Well, to think about that, what is the limit of h as x approaches -1 from the right-hand side? So as we
So h as x approaches -1 from the right-hand side would be, we're converging on a value of -2.
approach -1 from the right-hand side, it looks like h is approaching -2. So another way to think about it is, this is going to be equal to the limit as h of x approaches -2. And what direction is it approaching -2 from? Well, it's approaching -2 from values larger than -2. H of x is decreasing down from the right-hand side. It looks like h is approaching -2. So another way to think about it is, this is going to be equal to the limit as h of x approaches -2. And what direction is it approaching -2 from? Well, it's approaching -2 from values larger than -2. H of x is decreasing down to -2 as x approaches -1 from the right. So it's approaching from values larger than -2 of g of h of x. G of h of x. I'm color coding it to be able to keep track of things. And so this is analogous to saying, what is the limit as, if you think about it as x approaches -2 from the positive direction of g. Here, h is just the input into g. So the input into g is approaching -2 from above, from the right, I should say, from values larger than -2. And we can see that g is approaching 3. So this right over here is going to be equal to 3. Now let's take the limit as x approaches. So now
let's try this one ourselves. So let's take the limit then as x approaches -1 from the left of g of h of x. Right. So that will equal essentially the limit of h of x approaching what value? So coming in from the left on h of x, we're approaching a value of -3. And we're getting values that are less than. So we're going to -3 in the left-hand direction. So -3 with a superscript of a negative. Of g of h of x, right? And then what is the value then of, so in this case, right, what did he do here? He said, okay, he evaluated g at the limit approaching -2 from the positive direction. Okay, got you. So then he evaluated, so now we'll evaluate g approaching the limit of -3 from the left. So on g approaching the value of -3 from the left, we have a value of 3. And because these equal each other, the limit of g of h of x as x approaches -1 is 3.
Take the limit as x approaches -1 from the left of, first thing, -1 limit. It is approaching -3 from above, or we could say from values greater than -3. And then from above, or values greater than -3, is approaching -3. And it is approaching -3 from values greater than -3. It's going, h of x is approaching -3 from above.
That got me there.
As x approaches -1 from the left. So as x approaches -1 from the left, it looks like h is approaching -3. So we could say this is the limit as h of x is approaching -3, and it is approaching -3 from values greater than -3. It's going, h of x is approaching -3 from above, or we could say from values greater than -3, and then of g of h of x. So another way.
Okay, so I have my sign flipped on my superscript. So he's saying that as we approach the limit of -1 for h of x, as we approach x values of -1 for h of x, the limit would be we're approaching a value of -3. And we're doing so, our y values are getting smaller, but we mean that we were coming in from above, right? And so above in turn details a positive superscript. We're not coming at it from like below. Right, we're coming at it from above in both situations. That's why we have positive on both. Got you. And so then if we reevaluate of -3 coming at it from the right, well, it so happens to be 3 still.
Think about it. What is the right hand limit and the left hand limit in this case are both equal to 3. And so when the right hand and the left hand limit is equal to the same thing, we know that the limit is equal to internal function right over here of h of x.
Okay, one more vid.
So over here I have two functions that have been visually or graphically defined. On the left here I have the graph of g of x, and on the right here I have the graph of h of x.
Okay, let's try this. Okay, should we do it on a whiteboard so you guys can see too? Okay, let's try it. Hey, MS Man, how's it going? Hey, Fake. Thank you for coming in, dude. This is sick. I'm glad you like it. Appreciate you being here. Thank you guys for joining me. Just started following online lessons toward learning my first programming language or anything really, and really enjoying it for the last couple weeks. And seeing someone a bit ahead of me is super awesome. Keep going. Nice, dude. Yeah, follow along and learn along with me, man. Hey, Jose. All right, let's do this one. Okay. So the limit of g of h of x as x approaches 1. Okay? So let's first find, does the limit for h of x, what is the limit for h of x? Okay? So h of x, the limit as we approach 1 would be 2. Okay? Okay, in that case, now is g of x, now is g continuous at 2? No, it's not. So let's evaluate this directionally then, right? So it is g continuous. Oh, I'm not even writing this for you guys. We want to know the limit, oh god, of g of h of x as x approaches 1. Okay, so the limit, what's the limit of h of x? Well, this is going to be 2 as x approaches 1. Right? So then, is g of x continuous? G of x continuous at 2? No. So let's come at this from different directions. So then we want to evaluate the limit of g of h of x as x approaches 1 from the, let's start off with the positive direction. Okay, so as we come in from the positive direction, we converge on a value of 2. So in both cases, this equals to 2. So what this means is that the limit of h of x as it approaches 2 from the negative direction of g of h of x is equal to, so -2 here as we approach from the left or below. So on this one we're coming at it from below. So we're coming at it from below here. So then, do we want to reflect that as coming at as from the negative direction on g of x? Right, yes. Because we're coming at from below here. So then this evaluate, if we're coming in at x equals 1 from the left, because this is values that are getting, they're smaller, that are getting larger. Right. So then let's think here. We're approaching 1, right? Well, that would be 0. So is this then 0? As we approach 1, right, the function is hitting converging on 0 from the left. Oh, sorry, we're looking at the value of 2, my bad. So coming at 2 from the left, I'm sorry. Coming at 2 from the left. So, right, which would be negative 2. Sorry, it wasn't 0. So then, let's see here. Then we need to evaluate the other direction. So the limit of g of h of x as x approaches 1 from the negative direction. So as we approach 1, oh, I just did that from the negative. Oh my gosh, I'm trolling. Well, in both cases, we're coming at it from below, actually, so we get lucky here. Right? So if we evaluate this, as x approaches 1 from the left, for h of x, coming out from below, and we're converging on a value of 2 from below. So in both cases, it would be negative 2. Well, no, this is obviously 2 to the negative. So then it evaluates out to negative 2. So is the answer negative 2?
Right? Let's just figure out first the limit as x approaches 1 of h of x. Looks like h of x is approaching 2. And this is 0, but the limit we're approaching negative. Fully thought through it. Because what we could do is think about this limit in terms of both left-handed and right-handed limits. So let's think of it this way. Approaches 1 from the left-hand side of g of h of x. All right, when you think about it this way, if we're approaching 1 from the left, right over here, we see that we are approaching 2 from the left, I guess you could say, or we're approaching 2 from below. And so the thing that we are inputting into g of x is approaching 2 from below. So the thing that we are inputting into g is approaching 2 from below. So if you approach 2 from below, right over here, what is g approaching? It looks like g is approaching negative 2. So this looks like is what to g means that really approaches 2 does not exist. But
yes,
you just have to think in both situations, limit are the same. That is going to be your limit. It is equal to
woo!
2.
That's what I'm talking about, boys. That definitely just made it all feel better. You got that one right. All right, feeling good.
What we're going to do in this video is come up with a...
All right, hold on. We got to get some vibes going again. All right. Get ready for the 4 questions. Come on, boys. Get ready. 4 practice. I don't like this one. No, I don't like that one. I wanted more like.
I've been trying to configure this
since
field
we're
for an
not
hour,
dubstep.
but this CRM sucks.
Oh
He
no.
needs time to stay.
Okay. Okay. All right. We got 4 questions, guys. Here we go. Let's go. I'll turn it down a little bit. All right. We got 4 questions here. Let's go. All right. Functions g and h are graphed. Find the limit of g of h of x as x approaches -3. All right. So let's first, does the limit exist of a, let's find h of the limit as x approaches -3 of h of x is equal to, on h of x, as we approach -3, we converge on a limit of 3. It does exist. Check. All right. Next, we want to check, is g continuous at that mark? Yes, it is continuous. And so does that just mean that we get the value at that point? So what does that mean again? What does that mean again? So if g is continuous at that point, then we take g of the limit is equal to 2. So we find the value of g of x at x equals, the limit equals 3. So we find that at x equals, the limit as equals 3. Would it be 1? It is continuous at all points. So it's interesting, boys. He asked the question you asked, Mon? Oh, I didn't see it. My bad. There's a lot of chats going on.
Work goes smoothly when you know the right steps. With Asana, you
Oh,
can
killing the vibes. Come on.
and stay on track.
I'm not going to listen to that. Okay, so I wish I took better notes here. All right. So the limit does exist of h of x at -3, right? It's 2. Oh, sorry, no. H of x is here, right? So at -3, the limit does exist at 3. So is g continuous at x equals 3? Yes, it is continuous at x equals 3. So do we what just happened? What just happened? I just got hit by like an EMP. EMPO! Someone's got a kill streak on me. We back? No. It's frozen. Does chat work still? Yeah. Okay. Okay. We're good. We're good. We're good. Yeah. EMP not gonna work on me. Okay. So if the function is continuous at that point, then what does that resemble? Do we just take that value of 1? I kind of want to go back and look at his.
This viral productivity tool is shutting down. Well, sort of. This guy used to work at Facebook.
Okay, I'm curious. Let's say I want to say for composite function, if the inside function limit exists and it's continuous for the outside, then what does that tell you? If the inside function is not limiting exists and the outside function continue at the limit of the inside function. At the limit, essentially can pass through the continuous outer function. Okay, so then is it just, so we would say what is g of x at, what is g of 3? G of 3 is 1. Do we say 1 here, boys? What do we think? We say 1 here? I think we go for it. We gotta trust go for what we think. All right. Functions f and h are graphed. We are trying to find the limit. We're trying to find the limit of, as x approaches 0, of f of h of x. Okay? So what's the limit as x approaches 0 for our inside function? It does not exist. So let's evaluate this from the right hand. Okay. So what is our limit? So what is our limit as x approaches 0 from the left of f of h of x? Okay. Well, as we approach the left here, we approach from the left, we converge on a limit of 1. And we're doing that from above, the positive direction. So that will then convert our limit of h of x as it goes to 1 from the positive direction for f of h of x. Right? What we're then going to do is evaluate f at 1 from the right or above. So we're adding evaluating f of x at as we approach 1 from. Now here's the interesting part. Do we so as x approaches 0, we'll have positive 1 so as f approaches 1 from the positive direction, we're converging on a point of like uh-oh. Well, let's try the right then. So as h approaches 0 from the right, we're converging on a value of 5. So then this, and we're doing that from below. So the limit of f of h of x as h of x approaches 5 from the left h of x is h of x equal to 5. Well, we don't even have 5 on the axes here. We're trolling. So there is no limit at that point. It doesn't exist. Oh, so let's go back and evaluate. We're doing this the inverse, the wrong way. Okay, hold on, let's think here. So we need to go back and evaluate on the outside function, right? So let's, okay, hold on. So the limit doesn't exist. So we want to evaluate, okay, as we approach f of x from 0, 4. Huh. This one's interesting. So then, functions f and h are graphed. Find the limit of f of h of x as x approaches 0. Choose one answer. Okay, so the limit of f of h of x as x approaches 0. So for h of x, oh, I got another go-getter here I forgot about. Oh, no! Bruh. Pause. Pause. Whoa. That was bad. Oh no! It's everywhere. Oh my gosh. No, to get in my keyboard. Oh, that's such a bummer. It's like in my keyboard. No. I'll be right back. Crap.
fentanyl is closer than you think. Yep, literal record scratch for a record scratch moment. Maybe you're having a good night out, because fentanyl is only in so-called hard drugs, right? Actually, fentanyl has been found in party drugs like cocaine and ecstasy. And even the tiniest amount can be deadly. Get all the facts at factsfightfentanyl.org. Sponsored by the California Department of Public Health.
Oh boy. It struck it. The ogre turns against me. Alright, hopefully we're alright here. I think we're alright. I think I got most of it out. So, if you notice any sticky keys, we know why. Gosh. Something always gotta happen here. Okay, back to this. Back to this. If I close the email. Okay, so let's figure this. Let's see here. So as we go to show of h of x, the limit for h of x as we approach 0 does not exist. So the limit of h of x does not exist. So then let me ask, if the internal function this is annoying. Give me my ChatGPT. Just ask some questions. You're really not going to work for me. Okay. I'll say if the internal function of a composite limit function is if you have a composite function, you're evaluating x of a, if and only if x b. Only if is existent. So if the limit does exist, then you can't even apply the rule. So you have a sign, you have g of x consistent. So at 0, we just don't even have a value then. Is that what it's saying here? Right? And we don't even have a definition of any value. Okay, let's try this one. Heyo, Biomaniac. Kids were taking the AP Calc test because tests in school today. AP Calc BC test today in school today. Someone pulled the fire alarm. I had someone pull the fire alarm during one of my calculus exams as well. Yeah, hey Clark, I'm using VS Code to take my notes to the markdown here. Okay, let's try this one. Functions H and F are graphed. This will be the last one for tonight. Make it count, boys. Make it count. All right, let's turn up the tunes. Last one for tonight. Last question for tonight. And then we might do maybe a LeetCode. Maybe. We'll see. We'll go. Maybe we'll find an easy one. Last calc question of the night, boys. Come on, here we go. Find the limit of h as x approaches -3 of h of f of x. Here we go. All right. Find the limit x -3 of h of f of x. All right, let's first find the limit of as x approaches -3 of f of x. So as x approaches -3 for f of x, we do have a limit of 1. Right? So then is h continuous at 1? No, we have an asymptote at 1.
AI teammates can help level up your
Oh,
goals
come on. Don't
by
kill the
connecting them
vibe.
to relevant projects. So every team knows their role in the
No,
bigger picture. Asana,
stop
the
with
number
the
one
tech
AI work
ads.
management platform. Try for free
Stop
today
with the
at
crap
asana.com.
CRM tech ads, please. Okay. So then, is it continuous at 1? No, we have an asymptote at 1. So then, let's evaluate, well, as we go to infinity, does this limit also not exist? Because then if we evaluate coming at, okay, let's go like, what is this one? Let's evaluate then f of x at coming in at -3 from the left, coming in from above, while still you're going off towards infinity. Maybe another asymptote 2. Oh, this one's tricky. So then if the outside function has an asymptote at the limit of the limit value, inside function is this also. composite function where you're evaluating really. Assume that as x goes to a, g of x is equal to L. But f of x asymptote at x equals L. Is infinitely continuous. I think. Do we agree on this one? People are saying 1, people are saying 2, people are saying D and E. What are people thinking on this one? So the inner function has a limit at 1 for x at negative, as x approaches negative 3, right? So then the outer function is not continuous at that, and we can't, if we evaluate the directions, we just go off into infinity. So the open function of f of x. Mod. So you think. So Ahmad says he thinks his x equals 4 because you have a. So the limit of h of x as x approaches negative 3 is. Let's turn down the music a little bit. As x approaches negative 3 for f of x, the limit is 1. Right? And we're not continuous in h of x for a value of 1 for x. So if we evaluate the directions then, coming out from above, coming at 1 from above, the right would just lead off to infinity. Mike, I want to say D and E here. Yes. Woo! Come on, boys. We got that one. Okay, next one. Functions f and h are graphed. Find the limit as x approaches negative 2 of f of h of x. Okay? So h of x as x approaches negative 2 has a limit of 1, right? So the limit of h of x as x approaches negative 2 is equal to 1. So is our function continuous at x equals 1? Yes, it is. And it has a value of 1. They really didn't give us an example of a left and right. They're trying to trick me. They're trying to trick me, boys. I say 1 here. Fo, call me Wendy. Woo! Woo! All right, we'll do lesson 6 tomorrow. Woo! All right, we made it through that one. So I definitely need to update my notes. for the properties of these, right? Or composite. All right. Oh boy. What am I doing to myself? What am I doing to myself? Binary tree. What am I supposed to actually return? Right? If we do this one, right? Am I supposed to create a collection and do this? Am I supposed to output this? Or what do I return? I return the paths in any order. But do I... But do I create a string? No, those are just... What is it asking? Anybody know what it's asking for the format of the return? Return all root to leaf paths in any order. Do I have to do this? Come on, give me a better question, I guess. Should go bits one. We cherry picking now, boys. Which one to do? A perfect square is an integer that is the square of an integer. In other words, it is the product of some other integer with itself. Okay. You may not use any built-in functions such as square root. A perfect square is an integer that is the square of an integer, right? So it's just a square. In other words, it's a product of some integer with itself. So 4 times 4 equals 16. 16 is a perfect square. Is an integer that is the square of an integer. Okay, gotcha. So 4 squared is 16. There's no whole number that goes into. Okay, so then if we want to find a perfect square of a value, so if given a number like 16, I mean, obviously you know the perfect square is going to be within the first like what quartile of the value, like at least like the first probably like quarter. Could we use let's do this. Let's use binary search. Okay, let's say, okay, we got to remember how to set up a binary search here. Because we want to search for a value by having this, right? So let's say while num is greater than, oh, hold on, we'll go like this. Copy is equal to num, while copy is greater than, obviously, while copy, yeah, that's what we're setting up here, Justin, exactly. We picked up on that too. Good job, man. We just, yeah, nice. So now we got to remember how to actually set up the binary search. Okay, so we need to continuously reduce copy by half, while copy divided by integer division by 2 divided by 2 so if you get to 1 is greater than 1. So would we want to stop on 1? Because we don't even need to do another move down. Like at that point, it's not worth our time. Got to remember here. So we need to continuously reduce down our, come on, Mike, think, binary search. We need to continuously reduce down the integer by half, and then do some conditional check, right? So let's just forget about the loop for now. Let's just say if num times num is equal to num, we'll have to change these. We'll have to say like copy num. Or we could just say squared, right? So if the copy, see if we can zoom in. If copy squared, copy num is equal to num, and we'll set a copy num up here so we can keep reference. Right. If copy num squared is equal to the number indicated, then return true, right? Elif, so we'll just say, we'll initiate a square here. We'll say square is equal to copy num squared. We'll say if square is equal to num, return true. Elif square is less than think, Mike, think. If the square is less than, we need to increase, right? If the square is less than num we want to create like a range of a left and a right. Oh, come on. Think. So we need to, I usually do this through the list, but what if we're just doing it on a single value? So obviously we evaluate if the square is equal to the number we're looking for, we return true, that it's a perfect square. If it's not, we need to reduce the number down or change the number somehow. So we need to have so we say while copy num is greater than 0, meaning that we floor down, okay? We're going to take a square if square is greater than num. Do we want to say, well, integer division 2 here is greater than 0? So this will do that perform. No, we want to, well, copy num is greater than 0. We want to evaluate the square of the number. But what if we say like left we only want to, the thing is let me look up on my CS50. I do have some notes. Okay, think. How can we, I need to just remember, I know how to solve the problem, but we just need to figure out how to remember how to write a binary search here. So, if I say left is, if I initialize it left, what do I want the pointers to represent here? Because they're not list ranges, but they are, like, they're integer ranges that I want to evaluate over. I don't think I want to, like, slice either. no doors left. Don't give me an ad. Please don't give me an ad. Okay, so we need to take 16 and we need to reduce it by half and say, okay, 8 squared is that's 64, so we need to do it again. 4, so reduce by half. 4 squared, that's 16. Well, we got it. Okay, so 14 divided by 2 is 7, so we're 49. So you go down again, do 3 squared, 9. You don't hit it. So you just say copy is greater than 0 if num copy is greater than, no, copy, so we'll say square is equal to, if square is equals to nums, if square is equal to nums, then, or to num, then return true. The square, so right off the bat, and then we'll say the square is less than num, turn false. Else we're going to say that nums copy and we're going to return false. Okay, so what I think is while the nums copy is greater than 0, meaning that once you hit 0, you know you're done and you have no square here and you're done. But you probably won't even get there actually, because you can say, we could probably say while, and then say while nums copy is greater than 0, or say while we could put this condition up to here, right? We could say while nums copy squared is greater than num right, something like that. But let's just try it with what we have here. Because in this case, you don't even technically need to do a binary search. You can just reduce down by half. right? And then the 8, and then once, so like, for example, if I have like 16, if I have 16, I reduce it by half, I get 8. That's 8 times 8 is 64. So no, that's if it, well, it's greater than. So it'll continue forward. Once the square becomes less, then you don't have one, and if you ever hit it, you do it. But it's at least going to be down by half. So 9 floor down is equal to 4.5 is 4. Okay, so yeah, you maybe can't do this then because you have you end up skipping the 3. So what if I can you force round up and then so that would go to 4.5, that round up to 5. That would divide by 2. That would go 2.5, 3. And use ceiling. Python. Math.seal. So if I ceiling, you might be able to do it with ceiling this way, right? Which is interesting because in the case of 16, you would go down 8, you'd hit it. So instead of flooring, if you did ceiling, which is really interesting. Because then it would go 9, 4.5 to 5. 5 times 5 is 25. Nope. To 2.5 up to 3. 9 hit. I want to try it. I don't know. We'll see. Let's try it. Let's call math.ceiling on nums copy and 2. I'm curious. No. It passes quite a few though. Interesting. Okay. Back to the drawing board here. Okay. Let's go, let's do the classic approach. Left is equal to 1, right is equal to num. And we can say middle is equal to left plus right. Is it floored by 2? That would give you 17. Right, that would give you 17. And then 17 divided by 2 would obviously be 8.5. That would be floored down to 8. Okay, let's see. I can't remember if that's the correct way to do the middle, but okay, then let's say while what do we want to say? So do we want to compute a middle here inside the loop? Say while, let's take a middle point between the left and the right. So let's just whatever. So let's say square is equal to middle if square is equal to num. We're going to return true. If square is less than num, we're going to return false. And then if square is greater than num, if square is greater than num, then we need to set left to be middle plus 1. We want to search no. Right, search lines are always again. Okay, so I do have the middle right. So my condition is while left is less than or equal to, yeah, right. While left is less than or equal to right. Right, we never want it to go over the right. So left would become middle. No, we want to just reduce. Because if square becomes less than, then you can just return false right away, meaning that so middle is what we're flooring down, we're squaring that. So then at the middle value is what we're evaluating, which is, so it's first from the 16, it's going to be 8, which is 64. Okay, that doesn't work. So we need to have middle become 4. So left stays where it's at, and right becomes middle. Right, we never want to move left because we always want to find a number that's lower. Right? Hey, Anand, how's it going? So let's think about this. So we have a left of 1 and a right of number. On an example of, let's say for 16. Okay? So while left is, so that's fine. This will evaluate to true. We take a middle. This will come out to be 8. The square becomes 64. This doesn't evaluate. This doesn't evaluate. So we need to reduce down. We need to reduce down. Our square is bigger. So we need to move our evaluation. Right becomes middle, which would be 8. So 9. Floor down would be divided by 2 would be 4. Right becomes middle. No way. No! 100. Okay, let's think. So middle becomes 50. Middle becomes 50. So 50 squared obviously is too big. So 1 to 50 now is our search range. Now middle becomes 25. Middle becomes 25, which is not true, or which is still, okay, so which is still 1 to 25. Okay, we know it's in the range of 1 to 25. So we find the middle. No, we take 25 is now our new middle. 25 squared, okay, no. We reduce it down again. Now right becomes 25. 1 to 25. We find a middle between there. So 12.5, so 12. Square 144. No. It's too big. Reduce down. So if the square becomes less than, we don't want to return false. We want to make left. So in the case where we have 25 as our right and 1 is our left, we have 12 as our middle. 144. Now we have 1 as our left, 12 as our right. Now we have 13, 6.5 divided by floor would be 6. 6 and 6 is 36. So no, that's great. So now we want to make middle. Now we know we're between middle and the right value. So it would be between 6 and 12. Right. So we would want to make left equal to, do we want to make left equal to middle? Or do we want to make these to middle plus 1? Like, do we want to include middle again on the search? If we just say middle, no. So we do need to move this forward, plus 1. And do we need to move the bottom one forward too? And then this go -1. Right? So then if we have right go down by 1, so in the case of 100, let's go to the case of 16 here. 16, 1 to 16, okay, that goes in. Middle becomes 8. 64, okay, so we reduce, right now becomes 8. 7. Yeah, we do reduce it down. That still works. So we got null on 14. Okay. I think that's it. Yes! Woo! Oh yeah, baby. What's Mike Myers saying? We gotta look up Mike Myers. Oh, come on.
You know how Mr. Kensington feels about that.
Oh, behave. Yeah. Yeah, baby. Yeah.
Yeah, baby. That's what I'm talking about.
Baby. Yeah. Yeah, baby. Yeah.
Ah. All right, you guys. Nice LeetCode. Okay. Gotcha. So I wanted to try. I had a I wanted to at least give it a try. You know, just try to reduce it down in until. But I had my. So I knew that you needed to reduce it down, but I had this initial thought that maybe you could even use the ceiling to, and then maybe there's could be a trick to just skip immediately down, but it didn't work that way. So disregard that. But yeah, so we end up using the classic approach of left and right here. And then, the left will never cross over the right, and if it does, then you know, we take a middle, and then we did our evaluation, and then we checked to see if our number was true at that point. Cool. Yeah, baby. Feeling good. I did commit today on GitHub, didn't I? Let's check. Let's see here. I don't want my day to go away. Yes, I have a contribution today. Good. Good. Keeping the streak alive. Sometimes I miss the 17th apparently and the 6th, so but I always try to push it every day. If you guys haven't followed me on GitHub, follow me on GitHub. You can access it on my site, michaeldemon.com, which is the pinned comment here. All right, you guys, I think I'm going to head out tonight. Thank you guys so much for joining me here. We did a lot of stuff today. We did a hour-long session on Calc 1, going over, or more than an hour-long session on Calc 1, like an hour and a half, I think, or something like that, going over composite, or, functions or whatnot. What was it called? The composite limit. Yeah, like composite limit functions where you have a function within a function and evaluating a limit on that and what to do. So that was lesson 5. Tomorrow we'll do lesson 6 of Khan Academy's Calc 1. But yeah, thank you guys so much for joining me here. We need to continue on with SpectroSim. I'm going to try to do a good project session in one of our streams this weekend. So I like to do two-parters on the weekend. So I'm going to do a morning session, I think, come on Saturday. So I know a lot of people are international, East Coast, and so the Saturday morning session should be able to help get you guys in here. And so I will do a Saturday morning session, I believe, probably around 9 a.m., maybe 10 a.m. PST. So it will be more in the evening for those international friends. But which will be good, so you guys can be able to get in bed or early in the morning for you guys. And then what we'll do is we'll do a project session where we will start to kind of develop the front end and database of our SpectroSim. So we wrote the regular expression and the JSON parsing for actually getting the max absorption data out of the API request that we did in response via PubChem. So we extracted out that information and then used groups within the regex to actually get out the individual values, and which was cool. Can we collab on a project? Yes. So Anand, I have the Whackathon. We're currently scheduling a Whackathon, a community hackathon. We're calling it the Whackathon, where we're going to do a stream and we'll all work together on a project. I discussed it last night, kind of an idea actually I had for the project. So I kind of gave like a 15-minute spiel about that, but we can talk about it in the Discord. Go ahead and just message in the Wackathon community chat within the Discord, and we'll go ahead and get discussing some project ideas, and then we can all collaborate on the same day or something. So but we have to obviously schedule it and figure out what we're actually doing. But I do want to do that as like a special for the channel. Anyways, so make sure you guys do that. Join the Discord link down below. And then what else? Yeah, so for SpectroSim, we were able to get the actual information we wanted. Now what we're going to do is we're going to store it locally. So you don't see the channel. Try to, it might be hidden because a lot of the new channels get hidden. So hold on. If you go to your settings, you might have to enable it to be seen. I might need to do it here so everybody sees it no matter what. Let me see. Edit server settings, onboarding, default channels. Oh yeah, it's not enabled, my bad. All right, now you should see it. So like exit and reload your Discord. My bad. The onboarding has like, you have to specifically set it to show those. So if I make new ones, sometimes I forget. My bad. So no wonder no one's been chatting in there. It's been hidden this whole time. Mike, you're such a goof. I swear, dude. I can teach myself programming, but I just forget the simplest, stupid stuff sometimes. My bad. I did not enable visibility for the hashtag Wackathon. Hashtag open source. For the copy link. Wackathon. Open source. The whack open source and source control. Version control, my bad. Okay. Sorry about that. Yeah, I updated it so everybody will see it by default now. It wasn't enabled, my fault. My bad, my bad, my bad, my bad. My bad. Yeah, no wonder someone asked about version control in Pro Git, and I had a section, but they didn't see it, obviously. Oh, come on. All right, nice, Anand. Glad you're in here. Okay. Hey, Kakarot. How's it going? I appreciate you joining me here. All right, you guys, thank you so much for being here. I stream every single day. My name is Michael. I'm 26 years old. I have a degree in human biology and a minor in chemistry, and I've been teaching myself how to code and learn Python and programming for about 11 months now. I built various projects. You can look them up on my in the pinned comment in the chat. That's my personal website. I have various, we're currently working on another one of our chemistry simulators via spectroscopy simulator, and we're currently we actually wrote the algorithm already. We're currently kind of like got a lot of the meat of the project done. We just kind of need to build a front end, a database storage, and some conditionals to evaluate and how to manage that storage, and then it's done. But obviously that's easier said than done. The whole front end is going to be yeah. Yeah, Python, right? All right, you guys, thanks so much for joining me. I appreciate you guys being here this evening. Please leave a like and subscribe. I stream every single day. I teach myself. And please join the Discord and chat with me there where we can discuss the Whackathon, potential project idea to do there. And yeah, I'll see you guys later.